In section 9.3, we continue our discussion of significance testing, but this time we're going to use it to talk about population means. And in this first half, the first part of section 9.3, we'll talk about our conditions. When we're using a significance test with population means, we'll do some significance testing. We'll actually do some testing, and we'll show you how to apply the 4 steps to that. In the second part of this, in 932, we'll start comparing a two-sided test with confidence intervals, and we'll talk about paired data as well. All right, so in the last section, we talked about proportions, population proportions, and how when we did inference with population proportions, our sampling distribution of the p-hat is a z-value because our sampling distribution is normally distributed. So the p-hats fall on a distribution that is normally, we converted it to a standard normal distribution, which was another way of saying a z-score. Here, we're continuing to use a t-distribution like we did in 8.3 when we did a confidence intervals for means. Here, significance tests means we're still going to be stuck with a t distribution with n-1 degrees of freedom, because when we substitute our sample standard deviation S in place of sigma, which we have to assume is unknown in most cases, then the the x bar, the distribution of all possible samples of x bar, the sampling distribution of x bar, does not end up being normally distributed. It's a little flatter and a little more area in the tails. It ends up being a t distribution. So we'll see that again here, just like we saw in 8.3, here in 9.3. All right, so an example, in an earlier example, a company claimed to have developed a new AAA battery that lasts longer than its regular AAA batteries. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. A simple random sample of 15 new batteries lasted an average of 33.9 hours with a standard deviation of 9.8. So that 33.9 hours and that 9.8 hours, those are from the sample. So those are statistics, right? So that's the sample mean and the sample standard deviation from our sample of size 15. So really what this significance test is trying to do is, okay, we know that a standard battery lasts 30 hours. Now, not every battery is going to last exactly 30 hours. Some are going to be higher, some are going to be lower. If we took a sample of size 15, we know that 15, sample size of 15, has a sampling distribution, so the X bars from all of our samples of size 15 would vary. We know that they should be clustered around 30 hours, but some samples will have a mean that's higher than 30, some will have a lower than 30. That's the whole point of the sampling distribution of X bar. Now, what we have to figure out is how likely are we? Maybe the sample means would vary quite a bit, and maybe 33.9 hours is not that strange for even the old batteries. The old batteries last 30 hours, but wouldn't all the samples be exactly 30 hours? Some might be higher, some might be lower. So what we want to do is, what's the probability that we would get a sample of size 15 that would last 33.9 hours or more? That's really what we want to figure out with this significance test, right? So is there convincing evidence that the new batteries actually last longer on average, or could that have happened just by chance? right? We won't expect every sample to come back, even if they are the same. The new batteries and the old batteries last the same amount of time. So in other words, the new batteries basically fail. They're the same as the old ones. Even if they were the same, we would expect some variation in our sample data. We wouldn't expect every sample mean X bar to be exactly 30 hours when they are still 30 hours, right? They're going to vary quite a bit. So maybe that we got that 33.9 hours just by chance. What's the probability that could have happened? All right, so we want to do a significance test. So we first want to set up our null and alternative hypotheses. Remember that the null hypothesis is always set up with a it's equal to something, right? So here mu is going to be equal to the 30 hours. So in other words, the new batteries aren't any different than the old. So they're the same. There is no difference. And then if the new batteries are actually doing what they're supposed to be doing, they should be lasting for longer than 30 hours. And then one more last thing, we want to say what that mu is. So what is mu in this case? So it's the mean lifetime of the new batteries, right? We know what the old one is. We want to hoping that the new batteries last longer. So that's why the alternative says mu is greater than 30. All right, so the conditions for carrying out the significance test, well, really they're the same as the conditions that we used in 8.3 when we were doing confidence intervals. We want to make sure that the data comes from a random sample or a randomized experiment. Now we'll talk more about randomized experiments next chapter. Actually, we'll do some discussions of experiments at the end of this section as well when we go to paired data. The second condition is 10%, just like we saw before. And then the third is our sampling distribution normal? And if the population distribution is normal, then our sampling distribution is normal. 2, if our sampling size is over 30, then we know our sampling distribution will be normal. And of course, we say normal here, but because we do our substitution of our S for our sigma, we know that even though the sampling distribution in theory is normal, we know that our distribution will fall on a T distribution because of the substitution, taking sigma out and putting S in. And then the third case here for the normality is that if we don't have normal population distribution and our sample size is less than 30, then we simply are going to graph the sample data. And then we say that, say in your 4 steps, you're going to say that you're graphing the sample data. And then what about the graph? So what kind of graph did you make? And what about that graph tells you it is safe to proceed? Basically, yeah, a histogram or maybe a box plot. My go-to is probably a box plot. And you say there are no outliers and no strong skewness, so it's safe to proceed with our T procedures. All right, the test statistic, again, we're going to be looking at how far away in terms of standard deviations is our statistic from the parameter. And the standard deviation of the statistic, that on the bottom there, that is sigma. That's the same as the standard deviation of the sampling distribution of X bar. That's sigma divided by the square root of n. However, we're not going to know that sigma, right? So we have the statistic for us, in theory, would be Z is equal to X bar minus mu naught. That's the hypothesized mu value, divided by sigma over square root of n. But we don't know sigma. So instead, we're going to do a substitution. And once we put that S of X, the standard deviation of our sample in, then we know we have a T distribution. That the X bars in the sampling distribution will be not normally distributed, but it will end up being a T distribution with n minus 1 degrees of freedom. All right, so let's apply this to the battery problem. What would our T statistic be? Calculate that. If you need to pause the video, go ahead and do that. All right, so we plug in our values, our X bar minus our hypothesized mean value. And then the standard deviation divided by square root of n is on the bottom. And that ends up being a t-statistic of 1.54. And so the graph picture sort of shows you what's going on here. We're looking for what's the probability that that t would be that extreme or more on that t distribution. We have to think about sample size of 15, so degrees of freedom are 14. And you'll see when you go to row 14 in your table, you're typically not going to find the 1.54, but you'll find that it's between these two values. And so in the last chapter in 8.3, we were reading, we were going down and paying attention to the confidence interval, but here we want to read up and look at the probability values above those two values. So we know that our t-statistic, 1.54, falls between 1.345 and 1.761. So that's the t-statistic in the body. At the top is our p-values. So we know that our p-value is between 0.10 and 0.05, or really said the other way, usually the smaller one first, 0.05 and 0.1. So it's between 5 and 10%. And so that's the best that the t distribution table can tell us. But ultimately, that's all we need, right? It's between those two values. So it means, it's above 5%. All right. So in the t table, it gives us a range of p-values. And even though it gives us a range of values, we can still come up with the correct conclusion based on those p-values, right? Because we compare that always to a point, like say a 0.05. And so we can see that it's going to be above 0.05. It's between 0.05 and 0.1. Now, right now we're just doing a one-sided test. Our particular table has at the top a one-tailed and a two-tailed. Often you'll find the table, this table is different than the one in our textbook. Our textbook does not have a two-tailed column at the top. It just means, remember when we do a two-sided test, we have to double the probabilities. So that's why you see that the numbers on the two-tail column row are double the ones above it. All right. What else? We see that the degrees of freedom range from 1 down to 30, and then they sort of start jumping around. This particular table does not have 50 listed. If you look at the one in our book, it does have 50 as one of its options. So here we go 40, 60, 80, 100. I think our book does jumps from 30 to 40 to 50 to 60, 80, and then 100. But ultimately, if you're looking for a particular number of degrees of freedom and it's not listed in your table, then you have to go to the next lowest value, not don't go down on the table, but go up on the table. So if you had, say, 52 on this table here on our PowerPoint, 52, you would have to go, not rounding to 60, but you'd have to go back down to 40, or really up on the table to the next lowest value, which is up 1 to 40. Okay. And that is just a more conservative approach. It ends up giving you a value that's slightly bigger t value. So it's just more it's just a more conservative way of doing it. Okay. All right, and then the last thing is the values in our t table are all positive. So if you have a negative t value, you just get rid of it. You just get rid of the negative, and so you're pretend you're in the other positive side of the table, positive side of the distribution. It works just the same way because there's symmetry there. All right, so going back to this AAA battery, let's show how you could do the do part in your calculator. All right, so you would select the stat button and then cursor over to tests, and then choose the t-test. Now, this inference procedure for us is called a one sample t-test for mu. The TI people just call it t-test. Okay, so you would hit your stat button, go over to tests, and go down to t-test. And then in this case, they gave us the statistic. So in this problem, they gave us the X bar and the S. They didn't give us the actual list of data. So they didn't give us the 15 lifespan hours for each of the 15 batteries. If they did, we would put those in list one, and then we would choose, up here, we would choose data instead and tell it would ask, okay, so what list is your data in? And you would choose list one or whatever list you put that data in. But here they didn't give us the actual 15 data values. Instead, they gave us the X bar and the S. So we would choose stat and then choose the mu, the hypothesized mu value, the X bar, the standard deviation of the sample, and the sample size. Notice you're not telling it what the degrees of freedom are. The calculator is smart enough to know that it's going to subtract 1 from that. And then you want to choose your alternative. So our alternative hypothesis was that mu is greater than the hypothesized mu value of 30. So here, if you look, we choose mu value is greater than that hypothesized mu value, which is 30. All right, and then you hit calculate, and then it gives us the t statistic and the p value. So 3 things you should record down on your paper is the t statistic, the degrees of freedom, and then the p value. Now the calculator doesn't specifically give us the degrees of freedom, but you calculate that by subtracting 1. And then you want to draw some sort of picture, either labeled with the mu, hypothesized mu, and our X bar, or you can put a 0 and put the t value, either one. All right, you can also ask the calculator to draw instead of calculate, and it will draw the t distribution for you. It also gives us, if you notice, if you have it draw, it'll give you the t statistic as well as the p value. Now it doesn't say p value, it just says p. So you just have to be careful so that you know that this p is the p value or probability, not a proportion, because obviously we're doing means here, not proportions. So you just have to kind of keep your wits about you and know what that is that it's giving you. It doesn't actually say t statistic and p value, it just says t and p. All right, let's do another example. I believe you have this problem on a full sheet of paper in your PDF of your notes. Okay, a classic rock radio station claims to play an average of 50 minutes of music every hour. However, it seems that every time you turn to this station, there is a commercial playing. All right, to investigate their claim, you randomly select 12 different hours during the next week and record what the radio station plays in each of those 12 hours. Here are the number of minutes of music in each of these hours. So we have 12 data values. It's the number of minutes for each of the randomly selected hours that the radio station plays. All right, so we want to perform a one sample t-test for means with a significance level of alpha of 0.05. All right, so we want to do our 4-step process. We'll start with the state. Remember the state, we are trying to estimate, say what it is. We're trying to estimate, well, that's if we were doing a confidence interval. Here, we're going to set up our null and alternative hypotheses, say what the symbol is, in this case mu, what's mu stand for, and record the alpha level. So 3 things in the state. Pause the video and write that out if you want. All right, so for the state, we want to say that the null hypothesis is 50. That's what the radio station is claiming. We have a suspicion that they're playing more commercials than they're supposed to, and so we think that their average per hour, their average number of minutes per hour is less than 50. We're going to use an alpha of 0.05, and mu is the mean number of minutes per hour of music played that week by the radio station. So we're sampling from the entire 12 hours from the entire week. So it's how many minutes per hour on average they're playing for that entire week. All right, the plan, we want to state the inference procedure and check our conditions. So pause the video again and write that out. All right, so in the plan, we want to preform, and then we want to do a one sample t-test for means, and then the conditions. All right, so hours were randomly selected from the week. We selected 12. There are more, so we have to make sure that there are more than 120 hours in a week, and there are. And we don't know anything about the distribution of minutes per hour in the population. Our sample size is less than 30, it's 12, so we need to graph the sample data. Okay, so we would put all that data, those 12 data values, into, say, list 1, and we would plot them. And again, my go-to graph in this case is probably a box plot, a modified box plot that would show outliers if they were there. So clearly there are no outliers here. And so now what we would say is what we graphed, what kind of graph we made, and what about that graph tells us it's safe to proceed, right? So the box plot, okay, I'm saying what kind of graph I'm making, and then what is the data? The sample data shows no outliers or strong skewness. So the sampling distribution of X bar is approximately normal. Now we say that, but you have to remember, when we do our calculations, we don't know sigma, so we have to use a t distribution, not a normal distribution, but the theoretical sampling distribution of X bar will be approximately normal. So it is safe to proceed with our t distribution calculations. All right, the do. A couple things you could do. You already have that data in a list, so you can do a one var stat and get your X bar and your S. Remember here, we want to ignore that sigma of 2.69129 is if our calculator doesn't know whether the data we put in is population data or sample data. So it gives you sigma or S, and you just have to know that we're looking at S. We almost never look at our sigma in that case. So we have our X bar and our S. And so we could, by hand, calculate our t statistic, right? It's X bar minus mu, the hypothesized value of 50, and then divide it by S divided by square root of n. All right, so that gives us a t statistic of negative 2.567. Our degrees of freedom would be 11 because we have a sample size of 12, so 1 minus that. And then we would just go to our t table. And of course, we're not going to find that. First of all, it's negative, so ignore the negative and go look for 2.567 on row 11. And so we would find it between these two values. And so as a result, we go up to the head of the columns, and we would get our p values. So it's between these two values, which again, we know all of those are less than 0.05, which is our alpha. So we could make the correct decision based on that. All right, how could we do this using our calculators? Well, we could use data, or we could use stats, because since we've already run an X bar and a sigma, we could do a one var stat, and we would know our X bar and our sigma. Or we could really just use the data in list 1 and tell the calculator use data and say that, oh, our data is in list 1, and that would run the statistic for us. It would give us the statistic and the S. I mean, it would calculate all that for you. So you would still have to put in the hypothesized mu value, and you would need to choose your alternative hypothesis. Remember, our suspicion is that they're playing less than what they say they are, so we think that the alternative is mu is less than the hypothesized mu value of 50. All right. Once we hit calculate, in either case, whether we're doing data or stats, we get our p-value, get our t-statistic, and our p-value. Okay. Remember, too, that on your paper, regardless of what method you use, you need to give me three things. You need to give me the degrees of freedom, the t-statistic, or the range of the t-statistic and p-values up above. So t-statistic and the p-value. If you're using your calculator, it will give you an actual value, but if you're using the table, it's going to be a range of values, but you need to give me those. So three things: the number of degrees of freedom, t-statistic, p-value, and then the fourth thing is a normal, well, in this case, t-distribution, shaded and labeled. All right, and then finally, our conclusion should have three components to it, so work on that. Pause the video if you need to. Okay, so our conclusion, three parts: our p-value of 0.013 is less than our alpha of 0.05. Therefore, we're going to reject the null hypothesis. That's the second thing we have to say. And then the third thing is that there is convincing evidence that the true mean number of minutes per hour of music played that week is actually less than 50 minutes. All right, so just sort of a wrap up of what we've got here then. We have a t-statistic again. And again, most of the time we aren't going to be calculating this by hand. We're going to use our calculator and our t-test, and we won't have to actually calculate this, but you should know how to. We can certainly ask you questions on the quiz about this test, on the test about this. So remember too that we can have one-sided tests. So one-sided tests are if the alternative hypothesis is that mu is greater than a value, less than a value. Those are one-sided. Two-sided is if we don't have an inclination as to what direction the alternative should be, in which case we just say not equal to, and then we have two parts that are two areas, so the area or p-value will be double in those cases. All right, so this is your homework. And the last two problems, number 73 and number 75, are four-steppers. So that's due next class. Please make sure you work those last two problems as four-steppers so that you have plenty of practice for when you get problems like that on the free response questions of your test.